It's my great pleasure to introduce Professor Enrico Ramirez-Ruiz from the University of California, Santa Cruz, as the 2015 CRA Distinguished Lecturer. Enrico and I go way back, actually. We were grad students together at Cambridge. I was trying to think of an embarrassing or any story really to tell about our time at Cambridge. The only thing that came to mind was Enrico had basically, even though he was a grad student there, was pretty much acted like a postdoc. He floated from person to person, bouncing ideas, writing papers, and everyone was like, wow, we need to get on this Enrico gravy train of papers. And that was like all grad student wanted to do, because he was just all over the place, just generating science. And fortunately, before I left, I actually did write 2 papers with Enrico, so mission accomplished. Is what I would say. I actually left Cambridge a year before. That doesn't mean I'm any better, but I did leave a year before he did. He graduated in 2003, and then moved to a 5-year membership at the Institute for Advanced Study in Princeton. And because he's Enrico, he finished his 5-year membership in 4 years, which was pretty impressive. He then transitioned directly into a faculty job at the University of California, Santa Cruz, the Department of Astronomy and Astrophysics there, which by some measures is the sort of most productive astronomy department in the country. He's risen dramatically upwards through the ranks in a short time there. He is now a full professor and chair of the department at the University of California, Santa Cruz. Along his very steep trajectory, he's paused long enough to collect various prestigious awards, including a Sloan Fellowship, a Packard Fellowship, and was awarded an NSF Career Grant on the 5-year big awards. I, however, am not going as great. So we all have our little victories. Anyways, it's great fun having him back. He's a good friend of mine and an excellent scientist. And I'm really looking forward to his talk, which is a short and sweet title of Turning Stars into Gold. For those of you on campus, Enrico's visiting all week. He's going to give a technical seminar to the CRA on Thursday, and he'll be around as well. So if you bump into him, please say hello and chat, because he's actually quite friendly. All right, take it away.
Thank you. Thank you so much. It's really a great pleasure to be here. I owe actually a lot to Pablo Laguna in my career, so it's nice to come back here and interact with this amazing new center. So I'm going to be talking about turning stars into gold. It's a catchy title, but I will actually ultimately tell you where gold comes from and the current debates that we have today in the astrophysics community about its origin. So let's start. So as you know, since the beginning of written history, in humanity, gold has been valued not only because of its beautiful yellowish color, but primarily because of its ability to resist tarnish. It's an odd element number. It has, as you can see, 79 protons, 118 neutrons, and this big difference between protons and neutrons is going to become evident, and it's a very important problem in astrophysics, because in fact a lot of these elements are basically created by capturing neutrons. Yeah, so it's basically directly linked to the story I'm going to tell you. Gold has a melting point of about 1,000 degrees, which makes it extremely malleable. It's the most noble of all metals. What does that mean? That means that no other metal is less interactive to liquids and to gases, and no other metal is more valuable for its ability to basically resist corrosion. Yeah? That's why gold is being valued. And as you know, we've been through humanity, fought for gold. It's been an extremely important component of our history. But from a scientific perspective, we've been sort of enamored with the idea of how we make gold. And this is a nice picture of an alchemist in the 18th century. And today, basically, I'm going to tell you about my role of being an alchemist, but of course in the computer. Yeah? Because the conditions that you need to make gold can only be made astrophysically. So the densities that you need are so strong and the temperatures are so high that only very few cataclysmic events in the actually produce these very heavy elements. Gold is extremely rare. Yeah? It's about 1 part per billion mass. That means that for every atom of gold, there's about 1 million atoms of iron. So it's extremely, extremely rare. You can see here, these numbers are going to become central to our conversation. So in the universe, as you can see, 6 parts per billion. In the sun, it's about 1 part per billion. Meteorites actually have a significant enhancement in heavy metals, and that's one of the reasons why we want to go and mine asteroids, because they're extremely metal rich. Crustal rocks are slightly enriched. But in fact, the majority of the gold on Earth is in seawater. Yeah? But it's in such small amounts that it's been actually very difficult to economically feasibly extract gold from seawater. So if anyone in this audience comes with a brilliant idea to actually extract gold from seawater, please remember to give significant donations to the CRA so that it can last for. And in fact, humans, we are extremely metal rich. Yeah? We're about 50 times more metal rich than the universe and our sun. Yeah? So we have significant amounts of heavy elements, particularly of gold. So you'll be surprised, well, how is it possible that if really gold is only enhanced by 1 part in a billion, how is it that we find these gold deposits in these wide variety of sizes? Yeah? So these gold deposits are enhanced compared to the background by fractions of 10,000 and 100,000 times larger. Yeah? And that's one of the reasons why basically gold has played such an important role in our history. Why? Well, the reason is simple, because it's concentrated and transported in these crustal fluids. Yeah? So these high pressure chemical reactions basically concentrate gold and they transport it to the surface. And that's why we find these gold deposits which are significantly enhanced compared to the average. Yeah? And in fact, anyone that has actually looked through seawater, you can actually see the gold specks. Yeah? But there, you're significantly depleted on gold. Okay? So if you actually calculate the mass of all the gold that has ever been mined, is about the size of 10 school buses. It's about 165,000 tons. And about 85% of all that gold is actually stored in a vault. Yeah? So this first quote, I don't know if you have time to read of the fact that basically gold has no other use but just to be an accumulation of wealth component. It basically has no use in electronics, no significant use in electronics, and the majority of it is just basically on a vault somewhere. And I'll talk a little bit about the history of actually how gold got into the surface of the Earth at the end of the talk, which is actually quite interesting. I apologize, I don't know if you can read, but this is the price of gold per ounce in today's dollars. You can see here. Pablo and I are very much aware of this period, which of course the majority of the gold came from Mesoamerica, and it increased its value drastically in Europe. You can see here the French Revolution and then the Napoleonic Wars, California, the ability to extract gold in California, South Africa, World War I, and basically the First Depression, and then of course all the speculations in 1980s with high inflation of prices. Yeah? But in fact, apart from being an accumulation of wealth and being in some vault, gold has no obvious use. Yeah? So it's kind of surprising that it has shaped us as humanity the way that it has. My particular history with gold arise from the Mesoamerican culture. This is actually some beautiful travel companions that were found when you were buried. And the idea is actually rather beautiful. Gold doesn't tarnish, and therefore it was thought to basically accompany people for eternity, and you had to earn the ability of being accompanied through gold, by gold through through eternity. I can tell you that the pursuit of gold, particularly in these places, can have very different meanings, and it's basically a matter of pride. So UC Santa Cruz has no football team, so we're probably safe. And we have a mascot that is called the Slug, so we pose no threat whatsoever to you guys. Now, I want to date back to one of the first proposals of where gold came from, and it came from the Aztecs. The Aztecs thought that the sun was made of gold, and then in fact it was sweating, and the sweat of gold basically came to Earth and deposited these big fragments that I show you, which are drastically enhanced compared to the average. So let's sort of follow this idea of the Aztecs and said, well, how much gold there is in the sun? Yeah? So if you actually extract all the gold from the sun, you get the mass of the largest asteroid in the solar system, which is Ceres. Ceres is about 900 kilometers. This is a comparison, so you can imagine Ceres, if it was made of pure gold, with about $10 per gram, that's more or less the value of the sun in its gold content. Yeah. So again, as I was saying, 1 part per billion of the sun is made of gold. Yeah, and that more scale. So this is a spectrum from the sun. This is basically taking the light from the sun through a prism, basically. And what you see here are all the imprints of all the metal lines. And I would say that the majority, if not all, of the knowledge that we have about how elements form came from the sun. Yeah? So by understanding the spectra for the past 5 or so decades, astronomers have been able to infer the metal content of the universe, yeah, as it relates to our own solar system. So for us, this is our periodic table. Yeah? What is shown here is abundance in atoms as a function of atomic number. And clearly, as you can see, the majority of the baryonic mass in the universe is hydrogen and helium. We know that the majority of the mass was actually produced in the first 3 minutes in the history of the universe after the Big Bang. Yeah? So if you want to get an A+ on chemical evolution, you only need to know that the Big Bang produced basically hydrogen and helium, and that would explain, 99% of basically all the mass. There was some lithium form, but in very small quantities, as you can see here. So nuclear fusion is an extremely effective way in generating energy inside stars. Yeah? In fact, the temperatures inside stars are high enough that basically bring atoms together to such high velocities that actually nuclear fusion can take place. And nuclear fusion basically takes hydrogen and helium and burns it into heavier elements, all the way up to iron. Yeah? And in fact, that burning process is what we call an exothermic reaction. What does that mean? That reaction is giving energy to the system. That energy gives pressure to a star and allows it to fight its battle against gravity. Yeah? So in fact, the processing of heavy nuclei inside stars is in fact what keeps stars alive, fighting their battle against gravity. But something extremely interesting happens once you go to iron. And as you can see, iron is extremely abundant, and I'll tell you why. Well, iron is the most bound nuclei in the universe. So that means that if you want to generate elements that are heavier than iron, you have to give energy to the system. So it's no longer a viable alternative for a star to actually make elements that are heavier than iron Why? Because it has to give energy to the system. And remember, stars need to fight gravity and therefore need to get energy in this process. So that's not a feasible alternative. And then another impediment is that the Coulomb barrier, that means the repulsion, if you try to bring two very heavy nuclei together, it becomes progressively more difficult to do it. So basically no charge reactions are allowed to make nuclei heavier than iron. And this is just a side note that in fact the majority of the iron in your blood actually came from one of these supernovae explosions. So the silicon in your computer, the oxygen that we're breathing, and the iron in your blood are all synthesized inside stars. And as you can see, even though this is a minuscule part of the mass of the universe, they're essential for life. So that's why we care so deeply about these elements. So what can we do? Well, the universe actually does these elements, or it's thought to produce these elements by capturing neutrons. So neutrons have no Coulomb repulsion because they have no charge. So when you actually capture a neutron into a nuclei, it becomes basically radioactive and it beta decays. Okay? So this process comes at a price, and the price that you're paying is that you're producing these radioactive nuclei that quickly decay. And therefore, the assembly process becomes quite difficult. Something that I wanted to point out is that when you actually looked at stable nuclei, this line here, basically you're showing the number of neutrons versus the number of protons, and basically all the way to iron you have equal number of neutrons and protons, but once you go above iron you can see there's significant fraction of neutrons, and in fact the stability is only found when you have a significant neutron excess. So the majority of these nuclei from 26 above were actually produced by capturing neutrons. And that's why you're so far from these sort of alpha stability that we talked about. So astronomers are not very inventive, but there's two ways of actually capturing these neutrons. One is called the slow, and one is called the rapid. So slow with respect to what? Well, that means if you capture a neutron and you beta decay before you capture the next neutron, that's called slow. That means that the capture rate is slower compared to the beta decay. Okay? And that means that those nuclei are relatively stable. But really, to make most of the precious elements, you have to capture neutrons faster than you beta decay. So you're extremely away from equilibrium, and you're capturing all these neutrons basically when the nuclei are extremely radioactive. Okay? And you have to do it very fast. This shows the abundance patterns that we see from the slow process and the rapid process. This is my favorite peak, which is basically has platinum and gold. And the only way that you can make platinum and gold is by capturing neutrons very, very rapidly. So immediately, here speed has to do with density. If you want to capture neutrons fast, you need a very, very high density. If you want to capture neutrons slow, you can actually do it inside stars. So we know that the S process, the slow process, happens inside stars, but the rapid process needs the most extreme circumstances in the universe to take place. You need the highest neutron densities and temperatures of above 1 billion degrees. Okay? And in fact, for a long time, I would say, if you open a textbook and you ask, where these precious elements come from, they would all tell you that they come from supernova explosions. And they come basically very deep into the supernova explosion. This is when a massive star, about 10 times the mass of our sun, collapses. Why? Because it burns everything all the way to iron. As we were talking about, iron is the most stable element, so the star basically collapses at this point. And it forms a neutron star. I'll tell you about what a neutron star is in its core. And people thought, well, the R process comes from about a second after this collapse. Well, for the past 40 years, nuclear astrophysicists have been trying very, very hard to make the R process in this environments, and they basically failed. So what I come here to talk to you today is basically a new recipe for gold. Yeah? So if you're a modern alchemist like me, these are basically the ingredients that you need. You need 2 neutron stars, the densest object in the universe, not only 1, but 2. You need to merge them, and I'll tell you about why. That heats them up to about 1 billion degrees. It's necessary to make gold. And then when they merge, they collapse into a newly formed black hole. Yeah? So if that wasn't impressive enough, you have an extremely rare, extremely high energetic phenomena that ends up with the formation of a black hole generating gold. So I'll tell you a little bit about this. So this is sort of astronomy 101. We'll go over stellar evolution. We form a cloud. The cloud is able to collapse. Those clouds actually form what we call small stars or a large star. These stars are about the mass of the sun. They evolve through what we call a red giant phase. That means that they burn all the hydrogen. And when they start burning their helium, they actually expand drastically. They eject their envelope, and they produce these beautiful structures which we call planetary nebulae. Yeah? This is, of course, another mistake for astronomers, which thought that the object that formed in the core was actually a planet, but it's really not a planet, it's a white dwarf. A white dwarf is the size of the Earth, but the mass of the sun. Yeah? So a cup of dwarf matter weighs as much as 100 elephants. So they're extremely, extremely dense objects. These are not the ones that we're interested in. We're interested in very, very massive stars, about 10 times the size of our own sun, that when they collapse in these beautiful supernova explosions that produce a significant fraction of heavy elements, particularly iron, leave behind a neutron star in their cores, or if they're extremely massive, maybe a black hole. Okay, so you need 2 massive stars in a binary system for them to basically collapse and leave these 2 neutron stars. So neutron stars are amazing. They're the densest objects in the universe. They're the size of the San Francisco city if you are from the West Coast, or New York if you are from the East Coast, but I'm sure you can also put Atlanta here. And they're about 13 miles or so. They have the mass of the sun, yeah? And of course they have nuclear densities. I mean, these objects are so dense that the nuclei are basically almost touching each other. Yeah, they're the densest object in the universe, and they're supported by the strong force. So again, if you take a bucket of neutron star material, it weighs as much as Mount Everest. Yeah? So these are extremely, extremely dense objects. So what do we need? Well, we know that about 2% of all neutron stars are members of a binary. And basically, they don't evolve in isolation. Yeah? So you initially had 2 massive stars. You produce these 2 neutron star pairs. And these neutron star pairs, in fact, live these very, very interesting lives. And this is basically a topic of research where the CRA, it's a leader in the world trying to understand the gravitational wave signals that these objects basically emit as they go around. So these objects are so dense that the deformations of space and time are so strong that carry these gravitational waves. These gravitational waves basically carry both energy and angular momentum. So these objects are getting progressively closer to each other. This beautiful dance takes about 1 billion years to take place until the objects get close enough to each other that they basically merge. Yeah? So this is sort of an artist's impression of what happens. I'm going to tell you and show you in a second the sort of simulations that we do. And in fact, many people also in this room have done. So here you have 2 neutron stars about to merge. You have the 2 densest objects in the universe. Notice they're so compact. Notice the time scales is going to be actually in milliseconds. These objects basically touch each other. They produce, billion degree temperatures, eject what we call these tidal tails. They have to conserve angular momentum, so they have to eject material as they come closer and closer together. And it's really in these tidal tails that this material is synthesized and is actually ejected to the escape velocity of the system. And this object basically is too heavy to be supported, and it will ultimately collapse to a black hole. Yeah? So how much gold will one of these mergers produce? Here, the particles have been color-coded of where the gold is produced. The fraction actually that gets it away from the escape velocity, that it's able to leave the system, is a very small fraction of the mass here in the tidal tail. And in fact, the majority of the gold that is created ultimately falls back into the newly formed black hole. Yeah? So only about 1% of the mass of the system gets ejected. Yeah? So one of these events produces about a Jupiter mass of gold. Yeah? And if that's not impressive enough, this is more or less the amount of gold stored in about 6 million stars. So these events are rare, but they produce tons and tons of precious elements. So the initial prediction was, well, since these are so rare in the universe, there must be stars that happen very close to one of these events, and stars that happen to be formed very close to one of these events, after one of these events, and stars that form very far away. So there must be stars that are heavy metal stars that basically have tons of gold compared to the sun, and there are stars that are sort of anemic and have very little gold or precious elements. That was so what I'm going to tell you about is how we can try to test these ideas in a cosmological background, particularly thinking about how the Milky Way formed. So as you know, the history of the chemistry and the formation of heavy elements is intrinsically linked to the history of the universe. I already told you that over the first 3 minutes or so, most of the hydrogen and helium was formed. And then it took about 10 billion years for all the elements to be formed, and in fact, they continue to be formed constantly. So the metal content of the universe is constantly increasing. As we form new generations of stars. So as all of these explosive phenomena ejects the material into the gas phase, they get mixed into the gas phase, and then new stars are formed. And then these stars synthesize new material and so forth. So if you actually think about the history of every atom in your body, probably each atom in your body has resided inside about 10 different stars at what point in time. Probably all of the precious elements in your body has been reprocessed, particularly by one of these neutron star mergers, and by as many as 100 supernovae. So in your body, you have all of this memory that it's imprinted about how the universe evolved. Now, of course, astronomers cannot go to these exciting places when these neutron stars are about to merge. So what do? Well, we use the fossil record in our backyard. And what's our fossil record? The stars. Some of these stars that we see in our own Milky Way are so young that they formed when the universe was only a few % of its current age. So we basically try to understand the abundance property of these stars as a tracers. There are these historical fossils whose chemical evolution tells us, or chemical contest tells us, the history of the universe in their chemical composition. So this is our own Milky Way. And as you know, we have a thin disk where young stars are being formed. And we have this inner halo of stars. And then we have this outer halo of stars. And in general, we see the majority of young stars in the inner halo close to the thin disk, and relatively old stars in the outer halos. Stars that formed when the universe was almost pristine, when the metal content of the universe was extremely low. Why? Because only a few generations of star have been in play for that time that enriched, had very, very little time to enrich the universe with metals. So I'm going to show you two of my favorite stars. They have, again, not very interesting names. They usually come from surveys that find them. So these two stars are extremely interesting. They're sort of anemic stars. Why? Because they have about 100 times less iron than the sun. Yeah? So they have basically 1 part in 100 of the mass in metals of the sun. Yeah? So these stars are very, very old. But interestingly, one of these stars has a mass of gold that is about the mass of Pluto, and one of these stars has the mass of gold about the size of Herculina, who's a small asteroid in the solar system. So that means that the gold content in these stars is different by a factor of 1,000 between them. Even though the iron content and other metals are almost identical between them, one basically has 1,000 times more gold than the other. Yeah? So the simple idea is, of course, well, this one was either lucky or unlucky, depending on your perspective, of basically being born very close to where one of these neutron star mergers took place, while this one basically was born relatively far away from those. Yeah? And in the early universe, the mixing of metals was very inhomogeneous. So we tried to test this idea, and in order to do that, we have to make a Milky Way. So what I'm going to show you here is probably one of the state-of-the-art simulations of the formation of the Milky Way. This is done by Gabriela Guedes, a grad student at Santa Cruz. And what you see here in pink, you see the light emitted from the newly formed stars. The grayish background is basically gas. And the purple is sort of cold gas that is basically collapsing into stars. So as you can see, these new generations of stars are polluting this galaxy with metals. The Milky Way is actually an extremely interesting object because it had a relatively, so far, boring life. Yeah? Why? Because it didn't have a major merger. It didn't collide with a galaxy of its own mass. I would say this is about 1% of galaxies with the mass of the Milky Way have not had a major merger. So the Milky Way in that sense is extremely unique, but you know that that uniqueness is actually going to end when we actually merge with the Andromeda galaxy. So as you can see here, the Milky Way had a relatively boring life, and we're getting close. I didn't say this, but this is redshift, which is basically a unit of time for astronomers. And about this time, the sun forms in one of these arms. Yeah? So all of that formation history that you see is ultimately imprinted in the chemical composition of the stars that form the halo today in the Milky Way. Yeah? So the Milky Way's halo has this fossil record. Why? Because those stars are basically relatively low mass, and their age is the age of the universe. So they basically haven't died, and they've been there since they were formed. So something that we've been working is basically trying to understand whether or not we can link the astrophysical processes that create the elements with the enrichments of the stars that we see. Can we ultimately explain the fossil record of the Milky Way? And can these neutron star mergers be a viable alternative to producing most of the gold of the universe? So what I'm going to show you here is we inject these elements at the right rate and at the right amount of mass based on our simulations, and we basically looked at the results. So here, this is a rendering. This is basically the simulation, and this is the Milky Way today. So as you see, the simulation produces the right amount of mass, the right amount of dark matter, and it looks very much like the Milky Way. And what I show here are the fraction of stars that have strong enhancements of gold, the gold-enhanced stars. And as you can see, we can reproduce their frequency and their number density in the Milky Way. And this is, if you try to do this with supernova explosions, you fail drastically, because supernova explosions are very common and produce very little mass, and therefore produce very little variation from star to star. And I'll talk much more about this in the technical talk on Thursday. But ultimately, one of the successes is that we don't only understand the nuclear physics for making these elements very well, but we can actually put them into a framework of how the Milky Way formed and try to explain, what we see today in the fossil record. In the end of I wanted to say a few words about where the gold that we have here on Earth came from. And this is a very, very interesting question. So ultimately, the cloud that formed the sun and collapsed into the sun was enriched by these multiple generations of stars. Yeah? There's many, many astrophysical events that had taken place before all this gas was assembled. This gas, basically for today's standards, is extremely metal rich and produced the sun. From these disks, we created the planets. And naively, one expects that the metal contents of the planets is very similar to the metal contents of the initial sun. But what we forget is that when the Earth was actually produced, it was molten. Yeah? So what happened? Well, all the heavy elements actually sank into the center. I told you at the beginning of my talk that most of the gold in the surface of the Earth is in seawater. But in reality, 99% of all the gold on Earth is actually in the core. So when you actually looked at the abundance in the mantle of the Earth, it's enhanced by a factor of 10,000. How in the world did the mantle of the Earth was so drastically enhanced if initially all of the heavy elements actually sink into the center? Well, now geologists actually believe that the majority of heavy elements came from what we call the late bombardment. And this is the same bombardment that was responsible for making the moon and basically produced a very large collision between the Earth and a Venus-like object. Well, all of these meteorites, as I was telling you, are drastically enhanced in heavy elements and basically painted the surface of the Earth. And because the mantle is convective, those elements mixed into what it is today's mantle. So the majority of the heavy elements that we see today came from the late bombardment. And in fact, it is interesting to think about life as we know it on Earth, because life as we know it on Earth relies on the late bombardment. And in order to have a late bombardment, you actually have to have a Jupiter and a Saturn in the right place. Yeah? So you can possibly speculate that life as we know it, it's also intimately linked with the architecture of our own solar system. Yeah? If other solar systems were not as lucky as we were to have this episode of late bombardment, that means that the composition of other Earths will be very metal poor. Yeah? So if metals are an essential component of who we are, we owe it not only to these neutron star mergers and supernovae, but also to the exact architecture of our own solar system. Yeah. Now, this is not to say that life in Earths that have lower metal content cannot take place. No? Because of course we only know the biology of life as we know it on Earth. So I want to, before I open to questions, I wanted to tell you a story that was told by my grandfather, who was Olmeca. And Olmeca is a culture, a Mesoamerican culture in Mexico, which I think sort of ties nicely together gold with the story of why I'm here today. So he says, and I was 6 years old when he told me that story. He says, when you're conceived, yeah, he didn't call it your soul, but you call it your essence. Your essence is actually produced, and it rushes towards Earth to find you. Yeah? And its way in trying to find you, it breaks into all of these small pieces that basically get scattered everywhere on Earth. So he said, when you wake up the first time and you start to develop consciousness, you're actually going to feel extremely incomplete. Why? Because you're missing your essence. But he says, well, rather than being a problem, this is an opportunity. He said, why? Because those pieces, it's not that they fell into the ground and you have to go through life picking them up, they fell into other people. Yeah? And in order to recover your own essence, you basically have to share those pieces with other people to become more complete. So he says, the first thing that you should always remember is that every single person is valuable because they have a piece of your essence, and if you don't treat them with respect and care, you may never be complete. But it also puts the idea that some people have these huge pieces of your essence and some people have small pieces of your essence, but that we ultimately become one by basically taking advantage of those pieces. And in fact, this has been, for me, a very important theme in becoming a scientist, in which actually by interacting with other scientists, I have grown and I have become what I am thanks to others. So I want to stop here, and I hope that I can convince you the next time you see your gold ring that the process required to make these precious elements are extreme in the universe. They're rare. The majority of the gold content in the Earth came from one of these events, which hopefully will be detected by Laura soon in gravitational waves. They're the most extreme objects. Yeah? You require the two densest systems in the universe that you can think of. You have to mix them 1 billion degree Kelvin. You better stand out because they're going to produce a black hole in the process. But a certain fraction of their mass, about 1% of mass, produces the majority of heavy elements, and particularly precious elements in the universe today. And I'll stop there. Thank you.
Oodles of time for questions. So let's start.
In the graphs from before, you had the slow spectrum and the fast spectrum, but the slow spectrum didn't seem to have, it seemed to be more disjointed, didn't have lines where the gold and platinum is. Is that why the theme of the talk is gold, other than, obviously gold is pretty, but it's because gold and some platinum somewhat seems to be unique in this respect?
Yeah, let me see if I can. Well, I'll take you back to
Yeah, it's a while back.
the beginning. I have a better one to show you. This one.
Yeah.
So what is interesting, and I'll talk a little bit about this on how these elements are formed in detail when you do the nuclear astrophysics, is that about half of the elements are produced by this slow capture, and about half of the elements are produced by this rapid capture. Mm-hmm. And that not necessarily, and elements are produced by both, but in different proportions. Mm-hmm. Now, I chose gold in particular because, as you can see, for example, so europium here is the element that we use to actually, is the element that it's easier to see in stars. Mm-hmm. Why? Because it has a very strong oscillation strength, so that means that when light tries to leave the sun, it leaves a big imprint. Yeah, in the spectrum of the sun. So it's very deep line. So that's how we basically detect. And as you can see, this line is almost 99% our process. Mm-hmm. Both gold and platinum are also fully our process elements. But if I pick lead, for example, mm-hmm. Which is actually probably the most stable heavy element, is basically produced by the slow and the rapid process, mm-hmm. sort of in an 80-20% perspective. Okay. So they're both, they're not unique. And this has to do with basically how you capture them and the beta decay. But yeah, so you're absolutely right. I picked gold not only because it's pretty, I could have picked platinum, but gold has a much deeper history, I think, in humanity, and it resonates with people better. Okay. And those are basically 99% our process. Yeah, it's also lead, but then lead is lead poisoning, and you don't want to go into that. Yeah? It's not as attractive.
Yeah.
He's calling the shots, sorry.
So, what other astrophysical processes apart from neutron star motor can also lead to formation of
Yeah, so for the R process, you mean, no? So as I show you there, you need to beat this beta decay. So what that gives you is basically hundreds of milliseconds. So you need a process that operates in hundreds of millisecond timescales, that has nuclear densities and sort of billions degrees. So really your conclusion, and this was realized by Fred Hoyle and others 50 years ago, is that it had to be intimately related with neutron stars, either with the birth of a neutron star in a core collapse explosion or mergers. No? And mergers came as a proposal much later in the 70s, when people start realizing that these objects can actually in fact merge. But those are the two only options, no? Because those are the only two places in which you have the required densities and temperatures. So these are the two competing models. And it's interesting that if you calculate, for example, the rate multiplied by their mass per event, you can basically calculate what's the total mass of gold that they will produce today. And even though neutron star mergers are rarer, they produce more mass. Supernovae are more common, they produce much less. And if you multiply those two numbers, the rate by the mass per event, you get a total mass, and they both give you about the same number. So right now, that's why it's a big debate. But I can tell you that if you come to my talk on Thursday, I will show that supernova, from a nuclear perspective, they really fail miserably in trying to give you the right conditions. Yeah, and that's because they start with material that is not as neutron rich. While neutron star mergers are, in terms of nuclear physics, just ideal to make this R process.
In the fusing of these neutron stars, is there an upper limit to the heavier elements being created? Or are there just things that are, because it'd be the upper limit, that are so scarce or has a little half-life, you haven't seen it yet?
Yeah, so that's a great question. So basically, in the lab, because these elements are so short-lived, we have a record of the most heaviest element that we know today. If you come to my talk, I will basically show you that there's these three magic numbers in terms of nuclear structure. Yeah? And these basically are places where you get the highest abundance patterns. And in fact, there is the prediction that you can produce heavier elements, but the problem is that they're so short-lived that they're very difficult to study in the lab. But yes, all of the heaviest elements we know today were produced by neutron capture.
I apologize, I completely blanked.
All right, we can go for another.
How does the energy released by the fusion of two lighter elements compare to the energy released by the fission of two heavier elements in like a nuclear reactor, for example?
The fusion with what, sorry?
The fusion of two lighter elements in, say, a star, how does the energy of that compare to the energy released by the fission of two heavier elements in, say, a nuclear?
Oh, well. So if you take, hydrogen and helium, and naively you take 4 hydrogens and make a helium, you get about 0.7% of the rest mass energy, 0.7% of mc squared. Once you go to, say, carbon and oxygen and silicon burning, which actually produce iron, you're closer to like 0.8, 0.9%. So, more or less, that's sort of the figure that you should have in mind, that about, at most, 1% of mc squared is what you basically can get through these processes. When you merge two neutron stars, the energy that you get in return, it's about 0.1% of mc squared of the rest mass. Yeah? And a significant fraction of that energy is, in fact, carried in gravitational waves. And that's one of the reasons why we can actually see it, and in neutrinos, too. Yeah. So if you think about, are you a physics major? Or?
No.
So for example, a white dwarf, these objects that I tell you that are the size of the Earth and about the mass of the sun, they have a total binding energy. If basically the amount of work that it will take you to remove every single proton from the system, that it's about a fraction of 1% of mc squared. Yeah, so that is when you take a white dwarf and you explode it, there's basically nothing left. Why? Because the nuclear energy generation, as you said, by fusion is comparable to the amount of energy that holds it together, and then it will blow up. Once you get to a neutron star, basically gravity is the winner. No? Nuclear fusion and all of these energy processes cannot compete with gravity and the strong force, of course.
Hello.
So, is there a range of mergers in which the Laura doesn't detect enough mergers to explain the gold, or it takes too many to have an overabundance of gold?
Yeah, so of course, our sort of gold inventory of the Milky Way is not complete. So I would, I'm trying not to be technical, but of course he knows more or less the answer. So if you take the average rate of LIGO, yeah, I would say that you can easily produce all of the gold that we see today with ejected masses that are, maybe 5 times 10 to the minus 3 solar masses, which are sort of in the range of, what you get from your simulations. If LIGO starts going below the average predicted number, then I think mergers are in trouble, because basically they use, 5 times 10 to the minus 2 solar masses, so then it becomes a problem. So that's more or less the range. And so this is more, just to give you a feeling, one of these events in the average LIGO detection rate happens about once every million years in the Milky Way. So what Pablo is saying, if the event rate is not high enough, and it's a fraction of that, then you start running out of mass, because you cannot produce enough mass to explain the total gold content of the Milky Way today. So the number is about 1 per million year. And the optimistic LIGO rate is on the tens of events per mega year. And hopefully we'll see it in a few years. Is that right, Laura?
So is the mixing such that in a typical local region where you have stars, only a single one of these mergers contributes to the gold? You don't get any mixture from a couple of these events at all?
You can. That, of course, depends at the time that these objects form, no? So the mixing time of the Milky Way, it's more or less the rotational period, and that's about a gigayear. So this is extremely interesting. If you look at really metal-poor stars, basically their abundance variations are very much determined by the mixing. So during the first gigayears, you can have pockets that are extremely metal-rich and pockets that are extremely metal-poor, and the average metallicity in the first gigayear in the age of the Milky Way means nothing. You're absolutely right that once you look at stars that are much older, they have had time to basically mix significantly more. Now, in the simulations that we have, what we did is we looked for stars that had the same metallicity of the sun, that were born at the same distance to the sun today. We found about 100 or 1,000 of those. And then we looked at what is the average number of events that took to produce them. And statistically it was 1, but some of them had 3 or 4.
I remember my question. If you have the gold-rich stars, which are, according to the graph there, just kind of peppered around, does that mean that local to some of those stars would be a black hole that we would be otherwise unable to detect?
Yeah, so the problem is, so the reason why these stars are so well mixed is because stars interact with other stars and they end up mixing very effectively. So these stars have are so old that these dynamical processes were very effectively at mixing them together. And the same will happen with these, the black holes, or almost all the stars. No? So you do expect anything that is old, you expect them to be relatively well mixed within this halo of the Milky Way.
Okay.
So they don't there's no memory, and this is basically what Nacho was asking, which is basically, how much you retain memory of the number of events. And so there's the mixing of the stars, but also the mixing of the gas, no?
Okay, so just because we live in like a metal-rich solar system, there's no reason to think that there's a black hole kind of lurking around.
Yes, the majority, there are lots and lots of black holes around,
Right.
but they're usually black. Because they're not accreting, so therefore they're hard to see, but there are a lot of them, So for example, if you look at the density of stars that have a gold content that it's about 100 times that of the sun, or say 50 times that of the sun, they're significantly more rarer than the number of black holes in the Milky Way. I mean, we have a lot of these black holes. We just cannot see them.
Okay.
One question. Gold is found in concentrations on the Earth. Where does that concentration stem from? Does it come from the meteorite formation, meteor formation, the bombardment process itself, or processes on the Earth, in the Earth's crust?
Yeah, I think because the bombardment was so long ago, the Earth mantle was able to basically mix those elements very efficiently. So it basically comes from crustal fluids. So basically, in these very high pressure regions, basically golds get concentrated and then basically get steamed out. So when people actually look for mines, what they're looking is basically where these flows are ultimately depositing these heavy elements, which basically get concentrated by these, I would say, geophysical processes on Earth. So ultimately, I guess, if you were not long ago from the late bombardment, then there would have been a lot of anisotropies, but those got eradicated over time.
Thank you.
Yeah.
Okay. Steve did at the end.
Enrico, did you say that perhaps 100 supernovas or maybe neutron-star interactions could make elements, heavier elements in our bodies?
Mm-hmm.
So when a person is trying to say how old they are, they shouldn't say years anymore. They should say, well, I go back.
From the Big Bang, yeah.
So we're kind of a little bit of the Big Bang. And could somebody else in here have the same supernova or neutron stars that I have?
Most likely, yeah.
Then I'm almost a brother and sister. Is this the essence that you were?
Yeah. So for example, I'm writing this little article for National Geographic that it's named, the genealogy tree of every single atom in your body. And as it was alluded before, in reality, it's a statistical process. No? So basically statistically how many of these events happen. But if you think about it deeply, almost every single, almost every single element in your body was created in the Big Bang, and it was hydrogen and helium, and it got metamorphosis into heavier and heavier elements. So in fact, yes, I mean the memory of what you're made of comes back from the Big Bang. So, as most of
So maybe I'm really 13.7 billion years old,
yeah.
not just that's
Yeah, and those when the solar system evolves, those atoms will be incorporated into other generations of stars, and you'll thus live forever.
The future is bright.
Well, it's actually cold, but because the universe is expanding. But
We had a good stopping point there.
but the very near future is extremely bright, particularly if we all understand that we all come from the same genealogy and we're all equal. Yeah. Is that better?
That's a better
Okay. Thank you.